There is a fourth technique for solving quadratic equations that is sometimes very useful. It's not absolutely required, but let's take a look at how it works. It involves a technique you used earlier this term when you were looking at quadratic equations and their graphs. The technique is completing the square. So I'm going to show with a couple of examples how you can use the completing the square technique to solve a quadratic equation. There are basically 4 steps involved, and I'm going to go through them each with an example. The first step is to separate variable and constant terms to the opposite side. So here's a quadratic equation, 4x squared minus 24x minus 13 equals 0. We've got 2 variable terms and then a constant term. The idea is to move the constant term to the other side. So we're going to have 4x squared minus 24x, and then I'm going to give some room and then say equals, and then the negative 13 on the other side will be a positive 13. So there's the equation with the variable terms on one side, constant terms on the other. That's step 1. Step 2 is to divide both sides by the leading coefficient if a is not equal to 1. So here the leading coefficient is 4, so we're going to divide every term by 4, and that includes both sides. So I'm going to get x squared minus 6x equals 13/4. Now I recommend that you keep this as a fraction if it doesn't come out nicely. So let's keep that as 13/4 for now. Now this x squared and the 6x, you'll notice that I've left a little bit of space before the equals. There's a purpose for that, and we'll come to it next. The third step is to complete the square with the variable terms. Now remember how completing the square works is that we're going to create a binomial that is squared by taking half of the coefficient of the middle term. So, and then I'll undo the square on the variable, so to have the beginning of the binomial. So I'm going to take x squared and make it into an x in the binomial, and then half of that negative 6, half of negative 6 is negative 3, and that becomes my binomial, x minus 3 quantity squared. Now, at this point, I'm going to actually go back up and fill in that gap. How you fill that in is if you were to square this binomial out, x minus 3 times x minus 3, you would get the x squared, you would get the negative 6x, but you would also get this value that we just had, negative 3 quantity squared. So what I'm really doing here is I'm adding in an extra term on the left side of the equation. Technically, negative 3 squared is a positive 9. It's always going to be positive because you're going to be working with a square. So I've added a 9 to the left side, so I need to add that same number to the right. So I'm adding that positive 9 to the right side as well. This should kind of ring a bell, except it was when we did it with completing the square with quadratic functions, we kept everything on one side, and we had to think about signs a little bit more. This time, we're just going to add the same thing to both sides. And what that means is that I've changed my left side, and I need to go ahead and carry that down. So 13/4 plus 9, I need a common denominator. That will be 4. So the 9 is going to become 36 over 4. Add those 2 fractions together. So 13 over 4 plus 36 over 4 is 49 over 4. And now I have a perfect square, x minus 3 quantity squared, equal to a number. And we can use the square root property, which is step 4, to solve this equation. So we've been practicing using the square root property. We can do it here. So x minus 3, when we undo the square, we're going to square root the other side. So that's the square root of 49 over 4. And then don't forget, the price we pay for having the simpler technique is we have to get one solution that is positive, one solution that's negative. At least I should say on the value on the side opposite where you were undoing the square. So we have x minus 3 equals plus or minus square root of 49 over 4. Luckily, that fraction has a perfect square on top and bottom, so this is technically plus or minus 7/2. We can simplify that. And then to get x by itself, we just add 3 to both sides. Now, the tradition is when we add the 3 to both sides, we actually put it in front of the plus minus. So this is positive 3 plus minus 7/2. I'm going to come over here because I'm running out of room and work these out. So I'm going to have x is 3 plus 7/2, and then I'll have x equals 3 minus 7/2. getting a common denominator. That's 6 over 2 for the 3. So when I add those together, I get 13 halves for one solution. And the other solution, again, 6 over 2 for 3, minus 7 over 2 would give me negative 1/2. So I get my two solutions by using this alternative technique of completing the square. Some people love this technique. Some people are like, whoa, I'd much rather use the quadratic formula. I'm going to leave it up to you, but I think it's good to know there is like a fourth alternative technique. And every once in a while I find someone who just loves this technique and wants to use it all the time. All right, let's do two examples of this. The first example is just another quadratic equation, x squared plus 9x plus 2 equals 0. Remember, our first step is to keep the variable terms on one side and move the constant terms to the other. So I'm going to move that 2 to the right side and make it a negative 2. Then I'm going to go ahead and complete the square because I have no constant term to divide out of the x squared. So notice my a is 1. So at this point I can go ahead and complete the square. To do that, I'm going to bring down the x, so undo the square on the x, and then I always take half of that 9, okay, that coefficient for the x term. Now half of 9 is actually 9 halves. I do recommend that you go ahead and just keep it as a fraction for now. And then we're going to square that to add into what I've created. If you were to square this, you'd get the x squared, the plus 9x, and then you would get plus 81/4, because you're squaring that 9 halves to get back to what you've added into the equation. Now you need to add that to both sides, 81/4, and you're going to need to go ahead and perform this calculation on the right side. So remember, you have to add it to both sides. Whatever you've added in to create that perfect square, you need to add to both sides. Negative 2, I need a common denominator with the 81/4, so I think that would be negative 8/4. Double check it. Negative 8 divided by 4 is negative 2, so we've got a correct common denominator there. Plus 81/4. And then calculate those two fractions. Negative 8 plus 81 is 73/4. So we now have a perfect square, x plus 9 halves squared equal to 73/4. Because I've got a perfect square equal to a number, I can use the square root method to undo the square by getting two possible results, plus and minus the square root of 73/4. Now, unfortunately, 73 is not a perfect square, but I do have a perfect square in the denominator. So this becomes plus or minus the square root of 73 over 2. Notice there's no longer a square root in the denominator. And then to get x by itself, I'm going to move this positive 9 halves to the right side. And remember, the tradition is to put that value in front of the plus minus. So I'm going to get x equals negative 9 halves plus or minus the square root of 73 halves. And luckily we have a common denominator, so we can generally pull that into a single fraction. Negative 9 plus or minus the square root of 73 all over 2. And that answer, or answers, because there are two solutions there, tells us something. It looks really similar to the quadratic formula, and in fact, the completing square technique is how you create the quadratic formula. So let's take a moment to look at a general equation for a quadratic, ax squared plus bx plus c, and see how we get the quadratic formula out of it, okay, using the completing square process. So to solve this general quadratic equation using the completing square formula, you would go ahead and keep the variable terms on one side, ax squared plus bx, and move the constant term, which is c, to the other side. Now that's positive c becomes a negative c on the right side. Next, we would divide out the a, which is the leading coefficient, from every term. So now we just have x squared plus b over ax equals negative c over a. Now we're going to complete the square. So we want to have a perfect square here, a binomial. To get the binomial, we're going to undo the square on the x, and then we're going to always take half of the coefficient. Now this can be a little tricky sometimes for folks. When you take half of a fraction, you're really actually adding a factor of 2 to the denominator. B over a halved would be plus b over 2a. You can work that out with a little bit of fraction division. X plus b over 2a. Quantity squared would be our perfect square binomial. Now when we go to work this back out, and if you multiply this back out, you will get the x squared, you will get the b over ax, but you'll also get the square of this fraction we have in the binomial. You'll get b over 2a quantity squared. Okay, when we come back up. Now, we need to add this value, because it's new, to both sides. So I need to add it to the the right side, because I've added it to the left side. So this is going to be, and I'll go ahead and square the fraction as I write it down, b, the numerator squared would just simply be b squared over, the denominator is 2a. 2a times 2a is actually 4a squared. Watch the calculation there. You have to square both the 2 and the a. Now, we need to simplify this right side. Right now, we do not have a common denominator on these fractions. I have an a in one, and I have 4a squared in the other, so I need to multiply top and bottom of this first fraction by 4a to get that 4a squared on both. So if I write this first fraction, I'm going to have negative. Tradition is to write the number first, 4, and then when you're multiplying, do variables in alphabetical order. So that would be a times c over 4a squared plus b squared over 4ac, a squared rather. If we then continue to simplify this side, x plus b over 2a quantity squared stays the same. On the right side, we can add these because they have a common denominator of 4a squared, and tradition is to put the b squared in front and the minus 4ac after. Remember, addition can work is commutative, so you can either have negative 4ac first or the b squared first, as long as they continue to retain their signs. This should be looking very familiar at this stage. To where we're heading, which is the quadratic formula. To continue on, we want to undo the square. We've got this squared, so to undo the square, we square root x plus b over 2a equals, remember the plus or minus, square root of b squared minus 4ac over 4a squared. Now, the numerator doesn't square root. It's not a perfect square, but the denominator is a perfect square. So we can take the square root of 4, which is 2, and the square root of a squared, which is a. And there's a little bit extra stuff there, but I'm going to wave my hands and say that denominator does end up being 2a in the long run. And so we have a square root left in the numerator, but not in the denominator. So my fraction becomes the square root of b squared minus 4ac all over 2a. Plus or minus up front. Last step, move this positive b over 2a to the right side. When we do that, it's going to become a negative fraction. So x equals negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And as you know, with the quadratic formula, typically we would go ahead and write that all as a single fraction. I'm running a little out of room. Let me see if I can move this up just a tad, give myself room to finish this up. And so now we'll have x equals, keeping the common denominator, my entire numerator becomes negative b plus or minus the square root of b squared minus 4ac all over 2a, and that right there is the quadratic formula. So the quadratic formula actually comes from this completing square process. So the completing square process will do exactly what the quadratic formula does for you, which is solve quadratic equations. Just a fourth technique. If you like this technique, feel free to use it.